1.3 summary from the pre-calculus book in OpenStax. In this section, where I guess there's a couple of topics, but the main topic is this idea of rate of change, really the average rate of change. And it's one of those topics, actually everything you're talking about in this section, I got some good news and I got some bad news. The good news is it's relatively easy. And I don't mean that condescendingly, like I'm a math teacher, I get it, and it's easy for me. I mean, compared to a lot of the stuff you'll be seeing in this book, and even some stuff you've already seen, stuff's not that bad. This is relatively easy. However, this stuff is related to stuff that's very challenging. These concepts, turns out, can apply to calculus and to classes beyond calculus, stuff you wouldn't see till you were a graduate math student, like analysis. And so I think what happens is math teachers, myself included, see this stuff and get all excited and are like, oh my God, I remember this from grad school. I can't wait to teach these students some of this stuff I know. And the downside there is you end up talking about things that maybe students don't need to know at this point, and they take topics that are relatively easy and make them way harder than they need to be. My goal with this video is to try to talk about things at the level that is necessary to understand them for a pre-calculus class, which is probably what you're in if you're watching this thing. So the topics, the first topic, average rate of change. When I say this, y equals mx plus b, and I talk about this m right here, you know what I'm talking about? This whole idea of slope, maybe the slope of a line. If you know what that is, if you know how to calculate the slope of a line, you can calculate the average rate of change. It's the exact same thing. I have to be careful when I say exact, but let me give a quick example here. Here's a poorly drawn graph, and there's a poorly drawn line, and maybe this point right here has an x-coordinate of -1 and a y-coordinate of 1. And this point out here, I don't know, that's 2, and maybe this is, well, let's go out to 3 and call this, well, 1, 2, 3, maybe that's 4. I don't know, whatever. Call this x3 and y4. Here's a line, you have 2 points. Anytime you have 2 points on a line, you can calculate the slope of that line. Maybe this rings a bell. Maybe you use the letter M and you say something like rise over run. That sound familiar? Maybe. If it does, great. It's sort of like you count up how many and then over how many. If you want something a little bit more formulaic, you can say it's the change in y divided by the change in x. In other words, the difference in the 2 y coordinates divided by the difference in the 2 x coordinates. So you kind of arbitrarily call this one x1 and y1 and this x2 and y2. Doesn't matter which one you call which. Maybe if you're clever, you'd call this one x2 and y2. Since these numbers are larger than these numbers, when you subtract them, you'll avoid some negatives there. Call them whatever the hell you want. I'm going to call this x2 and this y2 and this x1 and this y1. So when I go plug everything into this formula, y2 is 4 minus y1 is 1. x2 is 3 minus x1 is -1. And if I do some subtraction here, 4 minus 1 is 3. 3 minus -1 is the same as 3 plus 1. It's 4. And 3/4 right here is the slope of this line. And you're like, yeah, slope of the line, that's not what I'm supposed to be learning in this section. True, but if you can do that, you can do everything you need with average rate of change. Because all the average rate of change does is instead of giving you a line, it gives you a curve. So I don't know, maybe this curve right here. And it calls it a function. Maybe it calls it the function f. And then it asks you the question. It says find the average rate of change, which to be lazy, I'll abbreviate AROC. Maybe it should be ARC because O is for of, and usually don't use that in acronym. But I kind of like AROC better than ARC. So I'm going to say AROC, average rate of change. I could ask you to find the average rate of change of this function f on the interval, to use the notation of the book. And then, I don't know, maybe I'd say from -1 to 3. What I'm doing here is I'm specifying 2 x values, and I'm asking you to find the average rate of change of this function that I drew in red right here on this interval. Turns out I've already done that, because the average rate of change is just the slope of the line connecting these 2 points. And the first point has an x-coordinate of -1, and the point on my red curve that has an x-coordinate of -1 is right here. And the next point has an x-coordinate of 3, and the point on my red curve that has an x-coordinate of 3 is right here. So even if you didn't have this line in blue, if I just started you out with this thing in red, and I didn't tell you any of the y-coordinates, I just told you the x-coordinates, you can figure out the average rate of change, because all you're doing is this calculation you've done above. Typically, you see a different formula. You see average rate of change equals f of x2 minus f of x1 divided by x2 minus x1. Whoa, hold on, that's not rise over run, that's totally different. It's really not, because the f of x2 is just asking you what's the y coordinate when the x coordinate is x2. What comes out of the machine when you put x2 into it? This right here is just another way of writing this right here. It's just using function notation. This is just the difference in the two y values divided by the difference in the two x values. It's the exact same thing you did up here. You get 3/4. And you'll do that in a number of different settings. I could draw you the graph of a function, and you could look at it, and I give you the x coordinates. You could figure out the y coordinates. I give you the equation of a function. I could say f of x equals, I don't know, x squared plus 3x minus 4. And I could ask you to find the average rate of change of that function on whatever interval I wanted. I'd give you two x coordinates. And you'd think down here and be like, all right, to do the average rate of change, I need the two x coordinates in my formula, but I also need the two y coordinates. But if I give you the rule of the function, if I tell you f of x equals x squared plus x minus 1, or whatever the hell I said a minute or two ago, you can figure out the two y coordinates by taking the x coordinates and plugging them in and seeing what comes out. Maybe I should do an example of that. Let's say g of x equals, maybe this should be a different color for a different example. G of x equals x squared minus 3x plus 4. And I think I change this every time, but whatever. And I might ask you to find the average rate of change of g on, and then pick your favorite interval. I don't know, 1, 3. Sure. You're like, average rate of change, that's this formula right here, which you can memorize if you got room in your head to memorize another formula, but I'd recommend against it. I'd recommend just remembering that average rate of change is just the slope, because you probably already got this thing memorized somewhere up in your head, and just reuse that rather than memorize a new formula. Maybe make the connection in your head that this notation really means the same thing as either of these notations up here. At any rate, the average rate of change. I need 4 things. I need f of x2, f of x1, x2, and x1. It makes no difference which of these you call x1 and x2. It's totally up to you. I'm going to arbitrarily call this x1 and this x2. So x2 minus x1, which would be in my denominator. And again, it doesn't matter what you name them, you just have to be consistent. Since I decided this is x1, when I want to find f of x1, I have to say that that is f of 1, because this right here is what I called x1 because it's right here in my formula. F of 1, how can I figure out what f of 1 is? Well, not f, I guess g of 1. Bummer. I should have used the letter g because I called my function g here because I had already used f earlier up here. So I guess really this average rate of change formula, it's kind of generic. Playing the role of f here is whatever function you're given. And maybe in the example that function was called g, that's fine. Anyways, g of x1, to figure out what I write right here in my formula, well, I'm just going to take 1 and put it into my function g. And we learned how to do that in section 1.1. We say, well, g of 1, here's the blueprint to figure out what comes out for any input into this function g. So if I change all the x's into 1s, I'd get 1 squared minus whatever 3 times 1 is, plus 4. I can evaluate that. 1 squared is 1. 3 times 1 is 3. So I got 1 minus 3 plus 4. I got 2. So g of 1 is 2. That in my formula goes right here. All right, that's this thing right here that I just figured out. Now I got to figure out this thing right here. I got to figure out what is g of x2. Well, no problem. I decided I'm going to call this thing x2. So to figure out g of x2, I just take this thing right here and plug it into my function g. And how do you do that? Well, you got the blueprint for g right here. Just change all the x's into 3's. 3 squared minus 3 times 3 plus 4. 3 squared is 9, minus 3 times 3 is also 9. So 9 minus 9 is 0, plus 4 more, I get 4. Goes right here in my formula. Do a little bit of subtraction, you get 2 over 2. Do a little division, you get 1. What that means is the average rate of change of this function on this interval is this right here. That's it. That's what you're going to be doing in this section. Average rate of change is probably the main topic of this section. You can figure out the average rate of change anytime you're given two x values, which you always will be, and you have the ability to find the two y values. How are you going to find the two y values? Well, either you're going to be supplied with an equation like this, or maybe a graph like this, some means of finding out the corresponding y values. You figure out the slope, you're done. That's it. That's all you're doing for average rate of change. It turns out that that's what you do when you calculate the derivative, which is a topic for calculus, which teachers get really excited about, and they really want to show you at this point to show you how powerful this is, because it's not especially exciting, anything that I've told you so far in this video. And calculus is exciting, at the risk of sounding like a nerdy math teacher. Calculus, the first calculus class, it'll blow your mind. It's really cool stuff. Okay, I'm going to stop this. I can feel people clicking and closing down this video. I better stop talking about average rate of change. I am going to talk a little bit about calculus, but I'm going to put it into a bonus video because I feel like the majority of people don't want to hear about it. That's okay. A couple more things to talk about. Increasing, decreasing, and extrema. These are easy topics, but you can make them really hard if you try to define them really carefully. Why would you define them really carefully? Because if you end up being a math major and if you end up taking graduate level math classes, you'll go into a class called analysis. And when you're in analysis, it will help to have very logical ways of deciding when a function is increasing and decreasing and when it's at one of its extrema. Really, that'll come into play in calculus and then after that. So it'll help to have these clever definitions of these things. But for the purposes of this class, I think just understanding what the hell they mean is what you should get at. And telling someone what they mean is easy. Trying to understand how the definitions that your book supplies you with are equivalent to what I'm about to tell you, that takes a little getting used to. My advice, understand what they mean. Listen to the next 2 minutes of this video. Understand what they mean. That's good. And then if you really want to excel, try to tie what I'm telling you now together with the definitions that are given in the book, which I'll end up this video by flipping through the book and showing you those definitions. Increasing and decreasing. They're exactly what you think they mean. Here's the graph of a function. Where is it increasing? It's increasing when the function is going up. And I don't mean up like straight up. I mean if you started out as far on the left as you could and you're a hiker and you have to end up as far on the right as you get. So you're kind of walking along this curve right here, and finally you get to here. Anywhere you're going uphill, the function's increasing. Anywhere that's drawn in green is where the function's increasing. If you ask somebody that wasn't in a math class where this function is increasing, they'd be totally fine. I bet everybody that's listening to this video could tell where this function is increasing and where it's decreasing. Totally fine. And then you go read the book. Nothing against your book. This is a perfectly good book. You go read any book in this section and they give you these really complicated definitions, which are really clever definitions for increasing and decreasing. But trying to apply those definitions ends up confusing a concept that you already knew. Graph is increasing when it's going up. It's decreasing when it's going down. This graph right here is increasing from -4 to -1. Note that I'm specifying the x coordinates of where it's increasing. And then again from 2 to 4. And it's decreasing from -1 to +2. Again, I'm specifying the x coordinates, not the y coordinates, where it's increasing and decreasing. That's it. That's increasing and decreasing. Last thing I want you to understand are what are called extrema. Maximums and minimums. They're exactly what you think they are. Maximums are kind of the highest points, minimums are the lowest points. There's a little bit more to it than that, because in this graph, for example, you might argue that this is the lowest point, but I might be like, no, you're wrong, it's not the lowest point, this point's lower. And you'd be like, oh, right, I didn't see that guy, I was kind of focusing on this. But there's something going on here, right? This deserves mention. Even if this point is lower than this point, something's going on here. So what we do is we define a couple different words. We talk about local minimums and maximums, and then also global minimums and maximums. A synonym for local is relative, and for global is absolute. So some books will use the words relative minimum, relative maximum, and then absolute minimum, absolute maximum. I believe your book uses local and global, so those are the words I will use. For a local minimum or maximum, we're talking about this point and this point. Anywhere the graph is at a hilltop, you're at a local maximum. Anywhere it's in a valley, you're at a local minimum. You don't got to be the lowest point on the entire graph. You just got to be lower than all of your immediate neighbors. You don't got to be the dumbest kid in the class. You just have to be dumber than everybody sitting right next to you is a way you can think about a local minimum. Or maybe it would have sounded better if I did that same stupid analogy for maximums. You don't got to be the smartest kid in the class, although in this case you are the smartest kid in the class. But you can imagine if this graph kept going up, there'd be some point up here that was way higher than this point. But that's okay. To be a local maximum, you don't have to be the highest point on the whole graph. You just got to be higher than all the guys right next to you. And what do you mean by right next to you? Well, that's where you start to get into some really complicated stuff. You talk about things like open sets. Topics that really I think are more appropriate for a higher level math class. So maybe just defining, I'm going to leave it as where I did. This point right here is a local maximum. This point right here is a local minimum. What about these guys? These endpoints. It's another point of confusion. Actually, before I get to the endpoints, let me talk about a global minimum and maximum. The global minimum and maximum means the highest point and the lowest point completely on the graph. So note that the lowest this graph ever gets is right here. This is a global minimum, or an absolute minimum. This guy right here. And you're like, okay, and this must be the global max. It's the last dot you didn't. Actually, it's not, right? This guy is higher than this guy. So this guy would also be my global max. Whoa, you can do that? You can have it be a local max and a global max? Sure, no problem. Totally fine. It's a local max because it's higher than any of its immediate neighbors. And it's a global maximum because it's higher than any other point on the graph. It's this point right here. So what's this then? It's nothing. It's just a point. Some books would argue that this point right here is a local maximum because it is higher than any of its neighbors. It doesn't have anybody sitting on the right of it, and all the kids sitting on the left of it are lower than it. So this point is higher than any of its neighbors. The technical definition for local maximum involves creating an open set. And really, okay, this is where you can get into really complicated stuff. Your book does not, really it avoids the question of whether this is a local maximum or not. It shows you graphs that have arrows at the end, so you don't have to worry about endpoints like this when we're dealing with local maximums and local minimums. Technically, the most agreed upon definition by most mathematicians would say that this is not a local maximum. It's an endpoint, and for whatever reason, a complicated reason that has to do with topics that are not pertinent to this class, endpoints are not local maximums or local minimums. They can still be global maximums and minimums, but not local maximums and local minimums. And why? It's really complicated. Maybe just take my word for it. A couple more things I want to mention. If this were an open circle, not a closed circle, then I couldn't say it was the global minimum, right? If it's an open circle, it's not on the graph. And you want to be like, oh, okay, so the point right next to it, kind of the next lowest point would win. But there is no next lowest point, which is really strange. The point that I want to make is that if this is an open circle, or if there is an arrow pointing down, I would have no global minimum, and that's totally fine too. It's possible for a graph to never obtain a global minimum. Similarly with a global maximum. If this arrow went up forever, there would be no global maximum, because any point you pick, I can go higher. You might think that the global maximum would therefore be like infinity or something, but it doesn't work out that way, because typically you want to specify where this global maximum occurs. And there's no x value that I could point to where it would take on that height. I'm making this more complicated than it needs to be. Increasing when it's going up, decreasing when it's going down. Local maximum anytime it's at a hilltop. Local minimum anytime it's down here in a valley. Global maximum when it's as high as it ever gets. Global minimum when it's as low as it ever gets. And for a really technical reason, which your book is really going to get around and not even ask you questions on, endpoints are not local maximums and local minimums, even if they appear to be. They can still be global maximums or minimums, but not local maximums or minimums. That's everything you need to get out of this section. I'm going to flip through the book, show you a couple pictures, and I'll call this video good. So we start out talking about average rate of change, and note it's the same formula as we saw. It's the change in y over the change of x. That looks a lot like our m formula. y2 minus y1 over x2 minus x1. Yeah, same thing. Here's another way of writing that. There's a lot of mathematical notation going on here, but it's just saying calculate the slope of the line that connects those 2 points. Calculate the slope of the line using those 2 points in there. It's not that bad. There's some applications of this. So you'll see lots of questions and putting things into words. Later on, you'll have some stuff about like force and different rate of change. But it's fine. You're always just taking the y coordinates and their difference over the difference in the x coordinates. That's it. That's all you'll ever do. So there's some pictures doing that stuff. Here's one where we're talking about force. Don't let that confuse you that we're talking about newtons now and charged particles. It's all good. It's just whatever the y coordinate is, whatever comes out of the function divided by whatever goes into the function. Same thing. A graph. It's increasing when it's going up. It's decreasing when it's going down. And it's that easy. But it's not that easy if you go reading down here. Right? This is complicated. F of b is greater than f of a wherever b is greater than a. Think about that for a little while, and maybe you can convince yourself that that's equivalent to what you think increasing is. But that's a very complicated way of describing increasing. That anytime my x-coordinate B is greater than my x-coordinate A, so B is further to the right of A, then f of B has to be greater than f of A. Okay, so the height of the point further to the right is higher than the height of the point further to the left. I guess that means increasing. It's a pretty damn complicated way of saying it, but it's true. This is the kind of definition that will help you when you're a graduate student, which a lot of you probably won't end up being. So a lot of you probably don't even care about that. But I guess it's good to expose some students to that at this point, and that's why you're reading that at this point. Same thing, increasing, decreasing. Note, we're talking about a local maximum, this point right here, local minimum, this point right here. The book doesn't make this a closed circle here. It gives you an arrow, so it can avoid the question of whether or not endpoints should be local maximums or local minimums. If you believe me, you should say endpoints are never local maximums or local minimums. But frankly, your book just kind of skirts it to the side because different authors say different things there. It doesn't really matter as long as you agree and treat the points as such. Local maximum, yeah, they're kind of making the point that if you switch from increasing to decreasing, you must have been at a local maximum, right? If you were hiking up a hill and then you started hiking down a hill, you were at the hill point, at the hilltop. Yeah, that's true. That's another different way of categorizing what a local maximum is. It ends up being a way that's very relevant once you take a calculus class. This picture right here describes what's called the first derivative test when you take a calculus class, but you'll relearn that when you take calculus, so I'm not going to spend a whole lot of time on it now. Again, here's some complicated ways of thinking about increasing, decreasing, and constant, not increasing or decreasing. And these are great if you can understand how if you can make these coincide with your intuitive understanding of increasing and decreasing and constant. Now we start talking about, here's more local minimums and maximums. And note, local minimums and maximums, they don't give you any endpoints because I don't want to deal with those. There's a local minimum right there. It's like a valley. There's a maximum right there. It's a hilltop. Hey, guess what? Your calculator can figure that stuff out too. There's a function in your calculator that'll figure that out. Maybe I'll do an example that shows you that. Same thing. There's the valley. There's the hilltop. These toolkit functions, we can talk about where they have local minimums and local maximums. Some of them don't have any. This one, for example, has a local minimum right here. We can talk about where they're increasing and decreasing. This one's always increasing. This one is decreasing, and then it starts increasing, for example. There's more increasing, decreasing. Note that now we switch and start talking about absolute maximum. So I guess they do use the word absolute, not global in this book. Now they give you endpoints because it's totally fine for an endpoint to be an absolute maximum. It's just when you're talking about relative maximums that is kind of iffy whether or not they should be considered, endpoint should be considered one of those. Here's some definitions for maximum and minimum for absolute. And these are good. If you can make these correspond with your intuitive understanding of absolute minimum and maximum, that's fantastic, especially if you have aspirations of being a math major or something. But if you don't, I don't know, maybe just understand what they mean intuitively and call that good. I guess that's everything I want to show you, so I'll end this video here.